the joint normal distribution. The joint normal is the most commonly used joint probability description in almost every branch of applied prob stats. And one of the main reasons of its popularity is the fact that this joint density is completely specified by only the first two moments, the mean vector and the covariance matrix. And it's also not a coincidence that if we have real observed data on a bunch of dependent random variables, it is the first two moments, the means, the variances, and the correlation coefficients are the statistics that we can most reliably get from the data. So this is the only named joint distribution that we will study in this lecture. Other joint distributions in many cases can be derived from or be approximated by the joint normal. So let's start with the bivariate normal. Let's recall that the random variable x is said to have a normal distribution with two parameters, the mean mu and the variance sigma squared, if its density function is given as you see on the screen. And there's a reason that we have q1 in the exponent because we are going to generalize that. The form of q1 we all remember, it's the inverse of the variance pre-multiplied and post-multiplied by the deviation of the value of the normal random variable from its mean. And you can also relate the arbitrary normal density with the standard normal density function, which is phi. Now, in a parallel manner, we can define the bivariate normal, where we introduce q2. So x1 and x2 have the non-singular bivariate normal distribution if their joint density looks like what you see on the screen, and q2 is written parallelly as we did for q1 is the inverse of the covariance matrix pre-multiplied and post-multiplied by x minus the mean vector. And note also that there is the square root of the determinant of the covariance matrix in the denominator. So we can expand this in terms of the 5 parameters that govern the density function, the two means, the two standard deviations, and the correlation coefficient. In standard form, the means are 0, the variances are 1, and it is governed by the single parameter rho. The bivariate normal distribution is said to be singular if the determinant of the covariance matrix is 0, or in other words, if the correlation coefficient is either plus or minus 1. Let's just look at the conditional and marginal distributions from the bivariate normal. So if we have the bivariate normal n2 given by it's the mean vector and the covariance matrix, then the marginal distribution of either one, x1 or x2, and regardless of the correlation coefficient between them, is univariate normal. So fx1 is normal mu1 sigma 1 squared, and likewise fx2 is normal mu2 sigma 2 squared. Unfortunately, and here I use the bouncing animation, the converse is not necessarily true. So if you have two marginal normals, if x1 and x2 are normal random variables and they have a certain degree of dependence between them, it is not necessary that their joint density function is going to be bivariate normal. And there are several quite famous examples of that, and they can be looked up from standard texts. And it's quite straightforward to show that from the bivariate normal we get the marginal density as the normal if we just integrate out one of the two random variables. So here we look at the marginal of x1 and we integrate the joint density in terms of x2, and if we do the right substitutions and if we go through the steps, then we are going to end up with the normal density function for x1, and here we started with the standard bivariate normal and we ended with the standard univariate normal. The same logic can be taken for the conditional density function. So if x is bivariate normal, we already know that the marginal density of either one is univariate normal. So if x is bivariate normal and we fix the value of say x2, then the conditional density of x1 is again normal. And that can simply be achieved by dividing the joint normal expression by the marginal density of x2 evaluated at the particular value b. If we go through the steps, it's interesting to see that the conditional density of x1 is normal with a mean that depends on b, the particular value that x2 has taken, and a variance that depends on the correlation coefficient. It doesn't depend on b. And it's also to be noted that that 1 minus rho squared, the conditional variance, is less than the original variance of 1. And if we generalize this for any bivariate normal where say x2 takes on the value little x2, then the conditional density of x1 is normal with the conditional mean which is given in terms of the original mean plus a correction factor which depends both on the deviation of x2 from its own mean and the correlation coefficient between the two random variables. The conditional variance depends on the original variance and the correlation coefficient, and it's easy to see that the conditional variance is less than the original variance, and it does not depend on what particular value the other one, x2, takes. Now let's move on to the multivariate normal distribution. Generalizing what we saw for the bivariate normal, so we have the mean vector mu, the covariance matrix V, and the n-dimensional random variable x has the multivariate normal distribution, the non-singular multivariate normal distribution, if the covariance matrix is positive definite and the joint PDF is of the form as we've seen before. So here we have Qn, V inverse is multiplied, pre and post multiplied by x minus mean vector. And note that we have the determinant, square root of the determinant in the denominator, and 2 pi raised to the power of n over 2. And it's often symbolically written as n subscript little n. A very important result is that the normal family is closed under linear combination. So if I start with this random vector x and combine them in with the help of coefficients C and add another B vector. As you see here, the new random vector that we get, y, which in general is m-dimensional, is also normal. And with the mean vector as you see on the screen, and the covariance matrix as also you see on the screen. So the mean of mu is multiplied with C, and that B vector is added to obtain the mean of Y, and the covariance matrix of X is pre-multiplied and post-multiplied by C. So in particular, and this is very useful for the purposes of Monte Carlo simulations, which we will see soon, is if we start with IID standard normals, so independent and identical distributed standard normals, which means that each of the z's, z1 up to zn, has a zero mean and unit standard deviation, and no correlation between any pair. So the covariance matrix of the z's is the identity matrix. So we can multiply the z's with the C matrix, the square matrix C, and add to that any vector mu. Then what we get is an n-dimensional normal y, whose mean vector is that vector that you added, and whose covariance matrix is C transpose. So this actually points to how we can generate dependent normals from independent standard normals when we do Monte Carlo simulations, and we'll see that soon. Let's complete this discussion with the conditional marginals as we did for the bivariate case. So let's partition the x vector, the n-dimensional x vector, which is multivariate normal, into x1 and x2 of dimensions k and n minus k respectively, and then the mean vector and the covariance matrix is also partitioned in a similar manner. So you have mu1 and mu2 and v11, v22 in the diagonal, and v12 and v21 in the off diagonal locations. So if we partition it that way, then each of these partitions, x1 and x2, are individually jointly normal. So x1 is nk and x2 is n minus k, with the mean vector mu1 and mu2 respectively, and the covariance matrix v11 and v22. Now x1 and x2, these two partitions would be independent of each other if and only if v12, all the elements are 0. The conditional distribution of x1 given x2 would again be k-dimensional joint normal, and as we saw in the bivariate case, the conditional mean vector is the original mean vector plus a correction term which depends on how far x2 is from its mean, and conditional covariance matrix, which is the original covariance matrix v11 and corrected by a term that you see on the screen. In the next few slides, we are going to look at some examples.